Hello everyone. Today we discuss section 6.4 about Taylor's theorem. The aim of this discussion is twofold. First, we would like to prove this Taylor theorem, which is another generalization of the mean value theorem. And the second aim is to discuss several applications of this theorem. So we discussed the mean value theorem in a previous section. It has several applications. We already mentioned the Cauchy mean value theorem, which is a generalization of the mean value theorem from one function to two functions. The Cauchy mean value theorem has that enormous power to lead into the L'Hopital rules, which are a very, very useful tool to determine the limit of function. Today, we discuss another generalization of the mean value theorem. So, the mean value theorem basically related to the equation fb minus fa divided by b minus a equal to f prime of c. So the Cauchy mean value theorem is based on the extension of generalizing one function to two functions. We can also consider the mean value theorem as a relation between the function f and its first derivative. In this perspective, we can generalize the mean value theorem in the following way. Instead of just one derivative, we can try to relate the function f to as many derivatives as possible. That actually the idea behind the Taylor theorem we are discussing today. So we first start with a definition. The Taylor polynomial of degree n for function f as x0 is given as follows. So Pn of x is equal to f of x0 plus f prime of x0 multiplies with x minus x0. So this is related to the first derivative of the function. Then the next term minus f double prime of x0 divided by 2 factorial and multiplies with x minus x0 squared. So this is related to the second derivative of the function. In a similar way, we can identify the n term in this n Taylor polynomial, which is the n derivative of the function f evaluated at x0 divided by n factorial and multiplied with x minus x0 to the n. So this is an expression involving the first n derivative of the function. And it is constructed in a special way, which we're going to see later. The basic Taylor theorem says that actually there is a way to relate the function f with its n Taylor polynomial. So the precise statement is as follows. Let n be a natural integer, I be an interval from a to b, and f be a function from the interval I to a set of all real numbers, such that all derivatives f prime, f double prime up to the n derivative of the function f are all continuous on the interval I, and the n plus 1 derivative exists on the open interval from A to B. If x0 is a number inside the interval I, then for any x inside the interval I, there exists a point C between x and f0 such that f of x equal to Pnx plus the n plus 1 derivative of the function f evaluated at some point C divided by n plus 1 factorial and multiplies with x minus x0 to the n plus 1. So in this diagram, you see that we have a given point x0. For any point x inside interval, there exists a point C so that we can relate the function f with Taylor polynomial, and the difference is identified. So in this case, here you have the Taylor polynomial of degree n, and the difference between the function and the Taylor polynomial degree n is an expression that is precisely determined. So this is the remainder term. Sometimes it's also called the error. Note that we can rewrite the mean value theorem in this way: fb minus fa equal to b minus a multiplied with f prime of c. That is, fb is equal to fa plus b minus a f prime of c. Then fa is essentially the polynomial, the Taylor polynomial of degree 0. And b minus a f prime of c is written as f prime of c divided by 1 factorial times b minus a to the 1. So we can see that the mean value theorem is essentially the Taylor theorem with n equal 0. So we see the Taylor theorem as another generalization of the mean value theorem. And this is a very good example of how we generalize results in mathematics. You can consider a statement from different perspectives. The Cauchy mean value theorem is an extension when we consider the statement as a result about one function and then generalizing it to two functions. If we use the perspective of the that relates the function to its first derivative, then we can generalize the theorem in another direction, leading to this Taylor theorem. Now, the proof here is basically in the same spirit as we saw earlier, using the roller theorem as the construction of some special function. The key point I would like to emphasize that the Taylor polynomial is constructed in a very special way, and it is seen by taking the derivative of this Taylor polynomial. So recall that the Taylor polynomial Pn of t equal to f of t plus x minus t, f prime of t, and so on. So if we take the derivative with respect to t, then this is equal to f prime of t plus minus 1 f prime of t plus x minus t times f double prime of t. So these two terms right here, let me use another color. These two terms right here basically come from the derivative of this term. And then you see that the first of these two terms cancel out the previous term. And then the second of these two terms cancel out the next term of the same column. That is, when you take the derivative of the Taylor polynomial, there is a lot of cancellation. And the Taylor polynomial is constructed in that way, in that special way, to obtain that level of cancellation so that you can simplify the derivative of the Taylor polynomial to be exactly one expression. Emphasize here. And using this observation, we can construct a special function and apply Rolle's theorem appropriately to obtain the result. Now, let me explain several applications of the Taylor theorem. The first application is to use the Taylor polynomial Pn of x to approximate the function f of x. This is very useful because the Taylor polynomial is a polynomial which can be computed numerically easily. On the other hand, the original function f of x might involve certain expression which is difficult to compute numerically. Furthermore, the error can be controlled by analyzing the remainder term. So recall the Taylor theorem is basically about this equation f of x equal to the Taylor polynomial plus this remainder term which involves the n plus 1 derivative of the function. Now here is an example. We consider the function f of x equal to the cube root of 1 over 1 plus x. So you see, this involves the cube root, and it is not easy to do calculation numerically. So we want to approximate the function by using the Taylor theorem. So in this case, we want to approximate f evaluated at point 3. So we choose x0 equals 0 and n equals 2 for simplicity. Then we compute the Taylor polynomial of degree 2. In order to compute the Taylor polynomial degree 2, we had to compute the derivative of the function of the first and second degree. So the first derivative of the function equal to 1/3 of times 1 plus x to the minus 2/3. When we evaluate this derivative as x0, so this is equal to f prime of 0, which is equal to 1/3 1 plus 0 equals 0. So this is 1 plus 0 equal 1. So this is just equal to 1/3. Now, the second derivative is equal to 1/3 times minus 2/3 times 1 plus x to the minus 5/3. So when we evaluate this expression at 0, then this is equal to 1/3 times minus 2/3, which equal to minus 2/9. So the Taylor polynomial of second degree is given by this expression, and we can evaluate it concretely. So f of 0 equal 1, f prime of 0 equal 1/3, so 1/3 x, and f double prime of 0 equal minus 2/9, so this is minus 2/9 times 2 factorial x squared, and this can be simplified further. So this is 1/9. So the approximation is Pn evaluated at point 3 equal to 1 plus 1/3 times 0.3 minus 19.3 squared, and you can numerically compute this expression very easily. It is equal to 1.09. We claim that this is pretty good approximation of the cubic root of 1 plus 0.3. Why? Because the error is a remainder term. Which is written here. The third derivative of the function evaluated at some point c divided by 3 factorial times x to the cube. So c here must be some number between 0 and 0.3. And the third derivative of the function here is evaluated to minus 2/9 times minus 5/3 times 1 plus x to the minus h/3. So this is equal to minus 10 divided by 27. So the error term here is minus 10 divided by 27 multiplies with 1 plus c to the minus h/3 divided by 3 factorial times 0.3 to the 3. And this is simplified to minus 9 divided by 81 times 0.3 to the 3 times 1 plus c to the minus h/3. Since c is between 0 and 0.3, we can estimate that 1 plus c to the minus h/3 is smaller than 1. This is a very rough estimate, but it's sufficient for our purpose, because now the error in absolute value is smaller than equal to 5 divided by 81 times 1 times, which is simplified to 1/600. So